equilibrium notes. This is a huge portion of the AP Chemistry exam. So make sure that you have a really, really good grasp of Ka, Kb, buffers, which we'll get to later. This is just your basic kind of introduction to the acid-base equilibrium. So starting out, we're going to start with our Arrhenius definition. This is the most basic definition of what an acid and a base is. And basically, acids, sorry, that's pretty lame. Acids will increase the hydrogen ion concentration when dissolved in water, and bases will increase the hydroxide ion concentration. And you can classify acids as mono, di, or triprotic, and the protic is referring to the hydrogen ion. Because if you think of a hydrogen ion, what a hydrogen atom is one proton with a little electron circling around, while if you have a positive hydrogen ion, that electron is gone and you're left with a proton. And so that's where mono, di, and triprotic come from. So like an example of a monoprotic acid would be hydrochloric, the strong acid. Diprotic, H2SO4. This is a strong acid. It has a weak acid component to it, and I'll explain that later. And then triprotic would be like H3PO4, phosphoric acid. And bases are either mono, di, or tribasic, also based on how many hydroxides they can generate, I guess is the right word. Monobasic example would be like sodium hydroxide. Dibasic example could be like zinc hydroxide. And tribasic could be like aluminum hydroxide. And acid-base strength is determined based on whether or not the acid or the base ionizes completely. If it ionizes completely, meaning that, like hydrochloric acid, for example, when you dissolve this in water, it completely ionizes into the hydrogen ions and the neutral chlorine ions. There will be none of the hydrogen still bonded to chlorines left in the solution. They are strong electrolytes because of this, because they do produce large amounts of ions. You need to memorize for the AP exam your 7 strong acids and your 8 strong bases. Your 7 strong acids are all of the halogen acids except for hydrofluoric acid. That one is a weak acid. But hydrochloric, hydrobromic, hydroiodic, those are all strong. And then all of the chlorine acids, so perchloric acid, chloric acid, chlorous acid, wait, no, that's not one, I'm sorry, just those 2, and then sulfuric acid and nitric acid. Make sure. 1, 2, 3, 4, 5, 6, 7. Yes, there's your 7 strong acids. And then your 8 strong bases are really easy to remember. They are the group 1 hydroxides and the, I can't remember if it's bottom half or top half of group 2. It is the bottom half of group 2. So, bottom of group 2. And by bottom, I'm referring to calcium, strontium, and barium. And again, well, not again, I have explained this actually. It's just the first hydroxide that is completely ionized, just like here in the sulfuric acid. It's only the first hydrogen that is completely ionized. And I'll kind of show you what I mean by that in a second. But yeah, diprotic acids, dibasic, strong guys, do not ionize completely, just their first hydrogen or hydroxide ionizes completely. So like if I'm showing you the ionization of sulfuric acid, H2SO4, what completely ionizes is the first hydrogen, and then you're left with this hydrogen sulfate ion. And then this hydrogen sulfate will further ionize, but only weakly, which means you kind of have this equilibrium situation going on, into another hydrogen ion and then the sulfate ion. So this is the reaction that makes sulfuric acid strong. This is just a weak acidic reaction. And just for future reference, if you have a strong acid reacting with a strong base, you are going to make a neutral salt and water. Now, Bronsted-Lowry, he was another definition of acids and bases that we use, and this is actually the one that does get used the most often at the AP Chemistry level, and it restricts the definition to hydrogens only. Basically that acids donate them and bases accept them, and it does allow us to classify a less traditional acid-base, like, ammonia. We can classify this as a base not because it has a hydroxide in it, although it does increase the hydroxide ion concentration, but because it can accept a hydrogen. And then conjugate acid-base pairs are basically two formulas in an equation whose formulas differ by hydrogen, and I will give you an example of this in just a second. And this is really strange to have it in this section right here. I should have had it on the last slide. I'm very sorry, I don't know how that happened. But strong acids and bases, we don't use the reversible arrow. We don't use, equilibrium expression where you have the concentration of products over the concentration of reactants like what we had in the general equilibrium notes. But all the other weak acids and bases, you can write equilibrium expressions for those. So let me just give you, refresh your memory a little bit on Bronsted-Lowry acids and bases and how you identify the acid, the base, and then the conjugate. So looking at this, we have HClO plus water yields this hydronium ion, which a hydronium ion is pretty much the same thing as a hydrogen ion. This one just indicates more clearly that it is dissolved in water. This one is just the hydrogen ion floating around. And then the hypochlorite ion, ClO with a -1 charge. So looking at this, what is the acid? Well, looking at these two guys, which one is going to give away a proton? Well, if you look over here, you see the ClO minus, which means this proton was given away, which makes this guy the acid. And then to find the base, we have to look, well, which guy accepts the proton. And so looking at water, you see over here it has accepted a proton, which makes it the base. And then what's left over of the acid after the proton has been donated is the conjugate base. And the reason that this is now called a base is because it is now capable of accepting a hydrogen, which makes it a base, but it's conjugate to our starting acid. And then the H3O plus now has an extra hydrogen ion here that it can give away, making it an acid, and because it is the acid in association with this base, it is the conjugate acid. And then coming down here to the bottom, we have the carbonate ion plus water, giving us a hydroxide ion and the bicarbonate or hydrogen carbonate ion. And so looking at this, to find the acid, you look at which one of these guys donated a proton. Well, this guy doesn't even have a hydrogen to donate, so that means that the water, in this case, is our acid. And the carbonate ion is the one that accepted the proton, so that makes him the base. And then coming over to the other side, once the water has given up its proton, what is left over is the conjugate base, because this guy is now capable of accepting a hydrogen. And then the bicarbonate ion has accepted the proton on behalf of the acid, and so it is now the conjugate acid because it has a proton to get rid of. So how many of you guys noticed here that in this situation water was a base, and in this situation water was an acid? Water can go both ways? Well, yes, it can, because it is something called an amphoteric substance. You know, if you remember your biology Latin prefixes, the prefix amph means like a dual state, like an amphibian lives in both an aquatic environment and a terrestrial environment. An amphoteric substance is something that can behave as either an acid or a base depending on whose company they're with. And so if an amphoteric substance is with a very strong acid, then it will probably behave as a base. Flip side of that, if an amphoteric substance is with a very strong base, then it will probably behave as an acid. And the easiest way, you will get a multiple choice about a question about an amphoteric substance on the chemistry AP exam. And so the easiest way to recognize your amphoteric substance is it is any compound that has hydrogens, and a lot of times it will have a negative charge. Water, of course, doesn't have a negative charge, but water is capable of becoming the hydronium ion if it accepts a proton, meaning it was an acid, or it can become a hydroxide ion if it donates a proton. So here's how water can go both ways. So if it accepts the proton, it's being a base, and if it donates the proton, it is being the acid. The bicarbonate ion that we just worked with, the HCO3 with the -1 charge, this one can also go both ways. It can accept a proton and become H2CO3, also known as carbonic acid. And so if it accepts the proton, that makes it a base. Or it can donate a proton, making it an acid, and return back to the carbonate ion. And so anything that has a hydrogen and a negative charge can behave as an amphoteric compound. And then, of course, water fits into that category as well. So at this point, I want to try to keep these videos a little shorter. I've kind of been getting a little bit long-winded. So I'm going to go ahead and break this up into a part 2 and quite possibly a part 3. So stay tuned.